Hey everyone, in this video we are going to discuss the RSA encryption algorithm. This algorithm was named after its inventors Ron Rivest, Adi Shamir and Leonard Edelman in 1977. It is a public key encryption technique and is considered as the most secure way of encryption. Now, before diving into the algorithm, let us first understand what encryption is and what problem led to the formulation of this algorithm. Suppose you want to tell your friend a secret. If you are right next to them, you can just whisper it. But if you are on the opposite sides of the country, that obviously won't work. You could write it down and mail it to them or use the phone, but each of these communication channels is insecure, and anyone with a strong enough motivation could easily intercept the message. One solution to prevent eavesdroppers from accessing message contents is to encrypt it. This basically means to add a code to the message which changes it into a jumbled mess. If your code is sufficiently complex, then the only people who will be able to access the original message are those who have access to the code. If you had a chance to share the code with your friend beforehand, then either of you can send an encrypted message at any time, knowing that you two are the only ones with the ability to read the message contents. But what if you didn't have a chance to share the code beforehand? This is one of the fundamental problems of cryptography, which has been addressed by public key encryption schemes like RSA. So, once a message has been encrypted with the public key, it can only be decrypted by another key known as the private key. Each RSA user has a key pair consisting of their public and private keys. Now, to understand the working of this algorithm, we first need to know a few mathematical concepts. The first one is the trapdoor function. RSA encryption works under the premise that the algorithm is easy to compute in one direction but almost impossible in reverse. As an example, if you were told that 7,01,111 is a product of two prime numbers, would you be able to figure out what those two numbers are? It would be a bit difficult, right? But if I ask you to flip things around, it becomes much easier. We can easily find out the product of these two numbers. But be aware that while the above example is hard for people to figure out, computers can do the operation in a trivial amount of time. Because of this, RSA uses much larger numbers. The size of the primes in a real RSA implementation varies, but in a 2048-bit RSA, they would come together to make keys that are 617 digits long. So basically, this property allows public keys to be shared without endangering the message or revealing the private key. They also allow data to be encrypted with one key in a way that can be only decrypted by the other key from the pair. The first step of encrypting a message with RSA is to generate the keys. To do this, we need two prime numbers, suppose x and y, which are selected with the primality test. The prime numbers need to be very large and also relatively far apart so that they are not easy to crack. We will use small numbers in examples only for the sake of simplicity. So suppose the numbers x and y are 907 and 773 respectively. Now we have the Carmichael's totient function lambda n equal to LCM of x minus 1 comma y minus 1, where n equal to x into y. On putting values of our x and y in this function, we get this value. Now that we have Carmichael's totient of our prime numbers, it's time to figure out our public key. Under RSA, public keys are made up of a prime number e as well as n. The number e can be anything between 1 and the value for lambda n, which in our example is 3,49,716. For this example, let's keep the numbers small to make calculations efficient. Say e equal to 11. Our final encrypted data is called the ciphertext C. We derive it from our plain text message M by applying the public key with the following formula: C equal to M to the power E mod N. We already have value of E and N. To keep things simple, Let's say that the message M that we want to encrypt and keep secret is just a single number 4. On plugging in everything in the formula, we get the value of C. So once data or a message has been turned into ciphertext with a public key, it can only be decrypted by the private key from the same key pair. Private keys are comprised of D and N. We already know N and the equation is used to find D, which is equal to 1 by E mod lambda N. Here 1 by E doesn't mean you have to divide 1 with E, it just represents the modular inverse, which can be calculated using the extended Euclidean algorithm, which is a bit out of scope of this video. So we can calculate the value of D. Finally, we put all the values to decrypt messages that were encrypted with our public key in the formula M equal to C to the power D mod N. So basically, the sender had a message which in our example was 4, but it can be anything, be it any message dealing with numbers or alphabets or both, because computers process the entire information in binary form. So we wanted to keep this message a secret. We applied the receiver's public key to it, which gave us the encrypted result. Now that it is encrypted, we can securely send the message in the form of ciphertext to the owner of the key pair. They are the only person who will be able to decrypt it with their private key. When they decrypt it, they will see the message that the receiver has really sent. Now, let's have a look at the algorithm's code. We'll start with the main function. So as we previously saw, we first need to generate or set two prime numbers. Suppose they are 3 and 7. N will be their product. Then we find the value of E with the help of Carmichael's totient function. So first we calculate the value of lambda, which is x minus 1 into y minus 1. Now the value of E should be between 1 and lambda, and E should be co-prime with lambda. So we initially set the value of E to 2 and then run a while loop until it acquires a value which is co-prime with lambda. And this is when the loop breaks. In order to check whether the values of E are co-prime with lambda or not, we use the GCD function shown here. Then we find the value of D such that it satisfies D into E equal to 1 plus K into lambda. Lambda is basically the totient. Now suppose the secret message that is to be sent is 12. We first calculate the message to the power E and then take its modulus with N to obtain the encrypted data, which is the ciphertext. Similarly, we apply the formula for decryption and obtain the decrypted data. Let's run the code and obtain the output. We can see here that the message sent and the decrypted data is same, which validates our algorithm.